Good afternoon, everybody. I hope you hear me well. I thank you, first of all, for attending this new EURADOS webinar dedicated to micro and nanodosimetry and its relation with biological damage. So my name is Carmen Villagrasa, and I am very pleased to welcome you as coordinator of this task, which is a part of the EURADOS working group 6 dedicated to computational dosimetry. So in this task, dealing with micro and nanodosimetry, the researchers work together in joint activities, which aim is to improve our understanding of the mechanism behind the initiation of biological effects generated by ionizing radiation. And those are, in fact, related to the topology of the energy deposition at the nanometric level. So to do that, in the frame of the computational dosimetry group, what we use are what we call Monte Carlo track structure codes. And in this task, we have activities that are related to the benchmark of these track structure codes, but also to evaluate the uncertainty associated to these results. Nevertheless, it is also very important to look at the experimental data that can be used to validate the simulation codes, but not only, also to identify measurable quantities at the nanometric and the micrometric scale that can be used to quantify this correlation between the radiation quality and the biological effects. That is the reason why in this task, experimental nano and microdosimetry are also considered, and you will see it especially in the first presentation of this webinar. So without further detail, I remind you the presentations that you will see in the webinar and that reflect the different aspects of micro and nanodosimetric research. We will start with the presentation of Dr. Hans Rabos, which is, by the way, the Working Group 6 chair, and he will be talking about the relation between experimental nanodosimetry and radiobiological effects. Then we will continue with Dr. Yann Perrault, that he will be presenting an example of track structure Monte Carlo code GN4 DNA for the mechanistic simulation of early rad-induced DNA damage. And we will finish with the presentation of Dr. Giorgio Baiocco that will present a new approach based on micro and nanodosimetry to characterize the effectiveness of a mixed radiation field. As you may know, you have next to you a chat. So the three presentations will follow each other, and at the end of the presentations, we will take care of answering some of the questions that you will put in the chat. You can see that you have different parts. If you could use the public chat to write your questions, this will facilitate the task for us, but so please, if you can, use the public chat. That's all. I give the floor to Dr. Hans Rabos for the first presentation, and I wish you a very interesting webinar.
Yes, thank you very much, Carmen. Good afternoon, everybody. Welcome to the first talk, which is on the relation between experimental nanodosimetry and radiobiological effects. I will start. Sorry. Okay, here we go. I will start with the question how particle track structure is characterized in microdosimetry and nanodosimetry. And I show you here in this cartoon a biological cell that is traversed by a charged particle track. The energy transfer points are these dots that are highlighted here. And if you have a situation like this, where the lateral extension of the track is smaller than the side size, we are in the realm of microdosimetry, where we characterize the particle track by the linear energy, Y, which is a stochastic quantity, and it's defined as the energy imparted to the target divided by the mean short length. The rationale for using the mean short length is that we don't know the geometrical relation between the particle track and the geometrical object. And energy imparted is actually calculated from a measurement of ionization. And this is possible because the number of ionizations is large enough so that we can use a mean energy per ionization to convert from ionization to energy. If we go to the other extreme and consider targets that are much smaller in dimension than the lateral extension of the track, then we are in the range of nanodosimetry, where an additional geometrical parameter comes into play, which is the distance indicated here as lowercase d of the track from the target. And here we have the problem that the conversion of ionization to linear energy fails, simply because the number of ionizations is so small that the use of an average energy per ionization does no longer work. So the quantities considered in nanodosimetry is therefore the ionization cluster size, the number of ionization in the target volume, that is also a stochastic quantity, and it is characterized by a frequency distribution, the frequency of a certain number of ionizations, and is conditional on the radiation quality. Instead of the frequency distribution, we can also look at cumulative distributions, which are basically the probabilities or frequencies of having at least a certain number k of ionizations, for instance. And like with any stochastic quantity, we can look at the moments of the statistical distribution that are associated with it. In the rest of the talk, I will only use a few of these possible nanodosimetric parameters of track structure. The first one is the mean number of ionizations in the site, denoted by m sub 1. The second is the probability that an ionization occurs in the site, which is denoted by f sub 1. The probability that an ionization cluster occurs in the site, which is a cluster is 2 or more ionization. And the probability for the occurrence of a complex ionization cluster, which is defined by 3 or more ionizations in the site. There have been a couple of instruments developed that are capable of measuring nanodosimetric properties of track structure. The first one was the so-called jet counter, developed at the Polish Nuclear Research Center, which basically mimics a nanometric target by a gas pulse, and the positive ions produced in that gas pulse are detected. The second instrument is the Star Trek counter, which has been developed at the Italian Nuclear Research Center in Legnaro. And this is a detector that detects electrons that are released when a primary particle interacts with the target volume. And this has been the first nanodosimeter that also allowed measurements at impact parameters different from 0, that is when the primary particle was not passing through the target volume. The third detector is the ion counter, which has originally been developed in a collaboration between the Weizmann Institute in Israel and the Loma Linda University in the United States, together with PTB in Germany. And it has been in operation at PTB and further developed, and is also counting positive ions, and has been developed to also allow measurements at impact parameters different from 0. And the ion counter, in addition, is capable of measuring with different operating gases, with nitrogen as is used in the jet counter, with propane as is used in the Star Trek counter, but also in water vapor and tetrahydrofuran, which is a chemical analog of the sugar group in the DNA backbone. These 3 nanodosimeters have been used in the frame of the BioQuad project to measure the same radiation quality, a number of same radiation qualities with the 3 detectors. And the graph on the left-hand side shows you the case of 72 MeV carbon ion for central passage through the target volume. The x-axis of the graph is the cluster size, and the y-axis is the frequency, cluster size frequency on a logarithmic scale. As you can see, the curves, the distributions are quite different. And this is simply due to the fact that the 3 nanometric detectors are mimicking different nanometric sites and also different geometries of the sites. However, even though these distributions are so different, if we look at the cumulative quantities and at the mean ionization cluster size, we get a completely different picture. And this is illustrated here on the right-hand side. This is a graph showing on the x-axis the mean cluster size, on the y-axis the probability for getting an ionization cluster. And basically the 3 curves shown, the 3 distributions shown on the left-hand side correspond to 3 symbols in the plot on the right-hand side. The colors code is the same, so blue is the Star Trek counter, red is the ion counter, and green is the jet counter. And the different symbols correspond to different types of primary particles, and the different points with the same symbol correspond to different particle energy. What you can see is that despite the differences between the 3 nanodosimeters, these data fall on the same curve. And this indicates that there seems to be a universal nanodosimetric relation between the mean ionization cluster size and the cumulative probabilities for having an ionization cluster or having complex ionization clusters. The same data that was shown in the previous slide on the right-hand side are now reproduced here on the left-hand side. And on the right-hand side, I compare radiobiological data, which are inactivation cross-sections of V79 cells as a function of the linear energy transfer. So linear energy transfer is shown on the x-axis, and it's the conventional macroscopic characteristic of particle track structure or radiation quality. And the y-axis is the inactivation cross-section at 5% survival, which has been calculated from survival curves of V79 cells that were irradiated either with protons, the data are shown here in blue, or carbon ions, which are the data in orange. And these data were taken from the GSI database BioPEDE. And as I said, calculated at 5% survival level, that is at a comparatively high dose value. So if we compare the 2 graphs on the left and on the right-hand side, there's some qualitative similarity. But on the quantitative side, we are comparing apples with oranges, because neither the x-axis nor the y-axis are comparable. So within the BioCrowd project, Valeria Conte did quite some analysis to make a quantitative comparison between the plots on the left and on the right-hand side. And the first step was to put the data on the right-hand side on the same x-axis as on the left-hand side. And in order to do that, she used the information about the particle energy and particle type and conducted some simulations. And using the diameter of the site as a free parameter and looking for the parameter value that would give a best qualitative agreement, a best relative agreement of the relative shape with the data on the left-hand side. And this was turned out to be for a cylinder that corresponds to a diameter of 1 nanometer in liquid water. So now that we have the inactivation cross-sections as a function of M1, we also have to take care of the y-axis. And there the approach was quite straightforward. It was a linear scaling factor was sought so that an optimum quantitative agreement is obtained between the data on the left-hand side and on the right-hand side. And this is shown here. So basically the data were just scaled. And if we plot them now on top of each other, we see that there's almost a perfect fit between the radiobiological data as a function of the mean ionization cluster size and the nanodosimetric probability for an ionization cluster scaled with a certain constant. This next graph shows the same information. It's basically the same data as before. But in addition here, also a comparison is made to what you get when you, instead of considering the probability for an ionization cluster, you just consider the probability for an ionization, which is the data shown as a dashed line. Or if instead of considering the data for an ionization cluster, you consider the nanodosimetric probability for a complex ionization cluster, which is the data for shown as dot dash curve. So it's quite evident that for this case, for 5% survival level, comparatively high doses, the F2 parameter, the nanodosimetric probability for an ionization cluster size, is the best choice that reproduces the radiobiological dependence on the radiation quality. But even more than that, this quantitative comparison gives you a scaling factor that has a value of 65 micrometers squared, which is very close to the geometrical cross-sectional area of the V79 cells that were studied in the radiobiological experiments. And this suggests that nanodosimetry indeed is related to the radiobiological effectiveness of radiation just by a geometrical factor that is related to the geometry of the cells. So, to summarize, the take-home messages are that nanodosimetric track structure characteristics are the ionization cluster size distributions, which depend on site and site location. That measurements with 3 different types of nanodosimeters showed a unique relation between the mean number of ionizations and the probability of ionization cluster formation. That the shape of this universal curve reproduces quantitatively the dependence of radiobiological effects on radiation quality. And of course, this analysis was even carried further, and it has also been used to derive parameters of the LQ model from nanodosimetric characteristics of track structure, and details of that can be found in the paper by Valeria Conte that I give here the citation of. And with that, I thank you for your attention and invite you to write your questions in the chat or send me an email afterwards. Thank you very much.
Thank you very much, Hans, for this very nice presentation. So for the moment, there are no questions in the chat, but I guess they are coming. You can maybe write the answer during the next presentation. So I give the floor now to Dr. Yann Perrault. Thank you.
Good afternoon. This presentation deals with the mechanistic simulation of early radio-induced DNA damage using track structure Monte Carlo codes. I will show you how to compute early DNA damage thanks to such codes, thanks to the results we obtained with a simulation chain we developed with the Giant-Fort DNA. Before starting, here is an example for which the understanding of radiation-induced effect is required. This example is related to the late effects of radiation therapy on healthy tissues, which is studied in the Rosiris program at IRSN, for example. So on one part, you have the irradiation setup that you can define by different parameters, such as particle, energy, dose rate, fractionation. And then you want to assess the risk that is evaluated also with other parameters. And the goal is to build in an adverse outcome pathway approach the different steps that lead from the irradiation to the risk. So the first step will be to perform the link between the irradiation and the early DNA damage that are measured preferentially by foci, and for which microdosimetry and nanodosimetry are very helpful since this kind of formalism will help us to get the DNA damage distribution and to have access to some kind of information such as the number of DSB, the yield, and the complexity. Then the other step will be to perform the link between the early DNA damage to other molecular mechanisms at other levels. And then we will perform the link between this mechanism to the risk. So as you can see, it is a multi-scale approach, starting from the physical interaction with target molecule to the biological effect. And track structure Monte Carlo codes are very helpful to cover the first microsecond of the irradiation, since track structure Monte Carlo codes will give you access to the detailed description of all the interaction of the particles to compute the direct effects, but also it will give you the capacity to compute the radiolysis of water and the action of radiolytic species to the DNA target in order to perform a correlation between what is simulated and what is measured experimentally. So among the different track structure Monte Carlo codes, I present you Giant4DNA. Giant4DNA is a project led by the Giant4DNA collaboration with the goal to extend the Giant4 simulation toolkit for computational radiobiology. So it is an open source code and fully available inside Giant4 distribution. It provides all the processes and the methods for the modeling of biological damage induced by ionizing radiation at the DNA scale, and ongoing developments include the physics with processes in liquid water and other materials, the physicochemistry and chemistry process for water radiolysis and the action of the radioactive species with DNA elements, and then target geometries at the molecular level. So among these different points, you need first the physics. So in Giant4, the physics is defined by several processes and models that you want to use in a given physics list. And on the table, I give you an example of a physics list for electron and proton and liquid water. As you can see, they cover a large range of large energy range. And Giant4DNA provides the cross-section first in liquid water, because this is the main medium of biological matter for electrons, protons, alpha, and few ions. Nevertheless, other materials are available. Thanks, for example, you have access to cross-section for DNA precursor, for electrons and protons. And if you are interested in, I invite you to have a look at the ICSD example. And in the next release of Giant4, also a cross-section for electrons in solid gold will be available. Ongoing developments cover cross-section for electrons in nitrogen and propane, which is a task performed in the EURADOS working group 6. Ongoing developments include also discrete electrons models in liquid water up to 10 MeV and discrete inelastic proton and hydrogen models from 100 MeV to 300 MeV. So after the physics stage, you have the chemistry stage in order to simulate the water radiolysis. The first developments of Giant4DNA provided a method, a step-by-step method, which is based on a particle continuum, which is particle continuum based, in which each individual molecule is simulated with a step-by-step Brownian dynamics, as you can see at the picture at the top right. In the picture at the top right. As you can see, all the species are simulated using Brownian diffusion, and when two radioactive species encounter, they react according to the table I give you in this slide. Nevertheless, keep in mind that this method is very time-consuming, and that's why recent developments in Geant4DNA propose a new method to deal with the chemistry, which is based on the independent reaction times that breaks the n-body problem into a two-body problem by comparing the reaction times for all pairs of radicals independently of the system. As you can see on the right, so the diffusion is not simulated. Nevertheless, you have a lookup table where all the reactions are sorted according the time, and then this approach will perform the first reaction, and then it will update only the table, which allow a sufficient gain in time. The next step is to have access to realistic geometry of the target, which is the DNA. And here I present you one kind of geometry obtained with the DNA Fabric software, which has been developed at RSN, and that allows the visualization and the construction of the whole genome, starting from the element basis, which is the pair of nucleotides. And the pair of nucleotides are combined together in order to form the double helix of DNA. And then this helix is twisted in order to form the chromatin fiber and to form several voxels that are combined together in order to form the whole chromatin fiber for each chromosome present in the cell nucleus. So the next step is to compute the damage. So you want to have access to the DNA strand break calculation and first the direct damage, which is computed when an energy deposit occurs in the sugar phosphate element of the DNA. When using a simulation toolkit, you have to keep in mind some limitations, and in this context, the main limitation come from the cross-section uncertainties. Because you have to know that data are missing at low energy for specific materials, and theoretical models are used for liquid water. And furthermore, one may wonder what is the mechanism at the origin of the strand break. It means that what deposited energy is required to perform a strand break, and this question is not so obvious. The second kind of damage are the indirect damage, where we look at the action of the hydroxyl radical to the sugar component of the DNA. Nevertheless, due to the geometrical configuration of the sugar, we don't take into account all the reaction, but only 40% of the reaction of the hydroxyl into sugar. And concerning the limitation, experimental data are mainly based on the evolution of the number of radioactive species in liquid water. It means that no data on the biologic target are available, and it's quite complex to benchmark this part of the simulation, knowing that benchmarking efforts are required since Geant4DNA proposed different simulation approaches, as I said, for the chemistry. The step-by-step one, which is more natural but too long, and the independent reaction times for which the approximations could perhaps not be adapted to all applications. So now you have computed the strand break, but you don't have at the moment access to the DNA damage because you have to convert the strand break to damage. So what is the damage? To answer, you have to analyze the configuration of the damage elements on each strand and classify them according to the configuration in order to give the definition of a damage. On the right, you have an example of a definition of damage from the position of different strand breaks. And concerning the limitations, benchmarking the DNA damage and DSB is not obvious because experimental data give foci induction a few minutes after irradiations, while I said that the track structure Monte Carlo code covers the first microsecond and so gives you the early DNA damage at 1 microsecond after the irradiation. Also, there is a lack of standardization of irradiation and measurement protocols. And also, we have a big difficulty to compare damage between different codes. That's why there is an initiative in order to standardize the way to present the different damage and to have a common language. Here is an example of benchmarking of our simulation tool for an irradiation of cell nucleus of fibroblast irradiated with protons at different LET. So in blue. On the left, you can see that the experimental data are very spread out. Nevertheless, it's important to see that our simulation tool and track structure Monte Carlo codes are able to reproduce the trend of the evolution of DSB induction according to the LET. On the right, you have a comparison of our results with other Monte Carlo codes, track structure Monte Carlo codes, for which you have to keep in mind that, as I said, so we have many limitations and we have some parameters to tune the results, and so we can always play with these parameters in order to fit the experimental data and to fit the other codes. Another important point is the impact of the geometry. I said you that you need a realistic geometry, and to prove you this importance, I show you here a model that we developed at RSN. You have to know that chromatin presents two compaction levels. The first one is heterochromatin, which is the condensate form of chromatin, and the second one is achromatin, which is the decondensate form of chromatin. So they can be observed in experiments, and so we developed a geometry that combines achromatin and heterochromatin. And on the right, you have some results. So in blue for a cell nucleus containing only heterochromatin, and in red for a nucleus containing a mixture of heterochromatin and achromatin according to proportions that were measured experimentally. And as you can see, DSB induction is more important in the mixture than in heterochromatin alone. And this is due to the fact that achromatin is more exposed to the effects of molecular species because it is more hydrated and has a fewer histones. To conclude, simulation of radiation-induced DNA damage based on track structure Monte Carlo codes are being used in a mechanistic or adverse outcome pathway approach in order to improve risk assessment for the use of ionizing radiation in medical application or low-dose exposure. Important progress has been achieved during the last decade in the development of this kind of simulation tools, including physical, physicochemical, and chemical stages. And G4DNA is an open access source code in continuous development in order to increase the knowledge and possibilities of the scientific community. Thanks a lot for your attention.
Thank you very much, Jan, for this clear and I hope useful presentation. So now we go to the third and last one from Dr. Giorgio Baiocco.
So good afternoon, everybody. This is the final presentation of the webinar, and it's somehow supposed to collect, let's say, and use the results and the concepts presented by my colleagues before, and to see how we can apply these concepts to a specific case, which is the calculation of the biological effectiveness of a mixed radiation field. So first of all, we need to define what a mixed radiation field is. The name tells it all. It is a radiation field composed by different kinds of radiation. And the point is that this is actually what we always encounter, because let's just think about an ion beam for therapy applications. If we have, for instance, a carbon beam, then the carbon ions will undergo reactions in the tissue, and they will induce the production of secondary species that are different from primary carbons. So we will end up with a mixed radiation field. And another example of application is the radiation environment in space, so for deep space missions, in which astronauts are exposed to this radiation environment that is by itself composed by different kinds of particles. So how do we want to use microdosimetry and nanodosimetry to explore and to characterize the biological effectiveness of a mixed field is the question. Well, I do not have to convince you that microdosimetry and nanodosimetry have a great potential. This has been shown by my colleagues before. And basically the point in their success is that they treat radiation on spatial scales that are the same as for particular structures of biological relevance, which are chromosomal domains for the micrometric size and the DNA double helix for the nanometric applications. So first of all, these kind of concepts, they are used, they can characterize the field. So in our case, they can characterize a mixed field, and they can as well be correlated with the biological outcome. So they can provide predictions of relative biological effectiveness. Let's discuss an example here about possible applications in therapy, in the planning of treatment for cancers, for instance. There are many works ongoing which are suggesting the implementation in a treatment plan calculation algorithm of the possibility to calculate, besides LET values, so the standard linear energy transfer values, which are somehow calculated always on a macroscopic scale, there are implementations being developed in which we can also calculate microdosimetric quantities, for instance, the dose mean linear energy. If this quantity can be computed, then this quantity can be used both to characterize the clinical beam from an experimental point of view, because microdosimeters are becoming available with reasonable sizes. That means that a particular kind of instrumentation can be used to characterize the field from an experimental point of view. And also, speaking about radiation in the treatment volume, we can use these quantities, like those mean linear energy, as mentioned, to optimize the treatment plan. In particular, when it comes to therapy applications for protons, one of the possibilities is that this quantity can be used to actually characterize the dose deposition, the energy deposition by proton beams, and to characterize what is actually known in the clinical practice, meaning that the biological effectiveness of a proton beam actually increases towards the end of the beam. So conventionally in the clinical practice, an RBE which is set to a fixed value of 1.1 is used, but we know, we have evidence that when the target region is close to a sensitive site in particular, the increase of the RBE of protons with the penetration of the protons can induce some first evidence of severe later reactions, like it is shown in this image, in which we actually observe some changes in MR images after treatment. And these changes can be harbinger for severe reactions, and this is of particular relevance when we think about proton therapy applications for pediatric patients. So if microdosimetry, for instance, provides us a quantity that can characterize either the field from an experimental point of view and also allow us to optimize even further the treatment plan, then of course microdosimetry has a great potential. So correlating micro or nanodosimetric quantities with the biological damage is something that it's also possible, and it has been discussed by Jan before. For instance, what I want to show you in this slide is a reference to a work which has been done by my collaboration, in which we actually calculated the DNA damage that has been induced by a wide series of particles in a wide energy range. And we have done this with PARTRAC, which is a biophysical code that is very similar to Gen4 DNA that has been introduced by Jan before. The idea now is that we can characterize the DNA damage induced by different particles as a function, for instance, of their LET. And the point of importance here is that this LET is an LET value calculated in a geometrical dimension, which is the one of a cell nucleus. So it's an LET value which is calculated in the micrometric regime, which means that this is really a concept very similar to the dose mean linear energy. If we plan to use the results, and by results here I mean the DNA damage induced as a function of LET in the cell nucleus, if we plan to use this kind of results in the therapy applications, then a very important point is to have these results readily available. So of course, we do not want to run full Monte Carlo simulations at each time we implement a treatment plan. And this is why I'm actually drawing your attention on this other work by my collaboration, in which we proposed an analytical fit of DNA damage results as a function of LET. So we provide particular analytical functions that are able, given a value of the LET, to obtain the corresponding kind of DNA damage. In this slide, the data are reported for double-strand break sites in the DNA. So now, how do we couple the different scales that are of interest in this kind of applications, and how do we actually compute the final effectiveness of the mixed field? Well, we, of course, have to use a particular code, like the code fits, for instance, but it's just one of the options. These codes are called transport codes because they actually transport radiation on the macroscopic scale. But still, some of these codes are able to compute microdosimetric quantities, even in microscopic region with some kind of analytical formulas that have been previously implemented. So basically, these codes can allow us to do the steps, let's say, that are necessary in terms of scale change. So we have in this representation, in this illustration, a simulation with a transport code, which is Gen4 in the specific case of a gantry. Then, of course, we have the patient phantom. And then we want to use the kind of information that can be extracted from fits to go to the cell level. What we basically propose in terms of an approach to calculate the effectiveness of the mixed field is, therefore, to use the transport code to derive for all particles, which means primary and secondary particles, because this is what the transport code does. So in the example I was talking about before, if you have a carbon beam which is fragmenting, then the transport code can give us information about primary carbons and secondary particles. So we want to derive for all these particles, all the particles that are in the field, which is their contribution to the total dose. We want to derive, and this is also possible with the transport code, an indicator of the density deposition, the energy density deposition by these particles at the micrometric scale, for instance, the dose mean linear energy. Then we might query a database with functions that are able to correlate this value of the dose mean linear energy to the DNA damage associated to that given particle at that specific linear energy value. And then, since we know how much of the total dose has been deposited by a specific particle, we can weigh the damage we obtain with the corresponding relative contribution to the total dose. So finally, we can sum up all damages, thus obtaining which is the damage from the mixed field in the region of interest. What I'm showing to you here is that this is actually an approach that has been tested, and it has been shown as a successful approach in the specific case of neutrons, for instance. Why am I introducing neutrons now? Well, basically because neutrons themselves, they always induce a mixed field. Neutrons, they do deposit energy in biological tissues because they induce reactions in which they accelerate charged particles. So the energy deposition ultimately can always be traced back to charged particles interactions. What we know about neutrons in terms of radiation biology and as a consequence of radiation protection is that neutron effectiveness is strongly dependent on neutron energy. So what you see in this plot here is the standard radiation weighting factors for neutrons as a function of neutron energy. You see there are actually different standards, the one from ICRP and the one from the US Nuclear Regulatory Commission, which is the one in blue. But still, the point of this approach here, of this application, the application presented in this work, is that if we apply this approach to calculate the effectiveness of the mixed field induced by neutrons, and we look, for instance, at the neutron-induced DNA damage that can be calculated, as I told you before, with this approach for the mixed field calculation of of DNA damage. Well, we obtain these these points here, which are the results of simulation. And the trend that is given by these points as a function of energy is actually resembling very much what we know from radiation protection. So the point is, this approach is actually working. It's giving us an indication of neutron biological effectiveness. And since neutron induce a mixed field, we consider that this approach is successful in the description of the effectiveness of a mixed field. So this is the RBE evaluation, considering a specific kind of DNA damage induced by neutrons as a function of their energy. And as you see, the trend is very similar to the one we know from radiation protection. This slide is actually suggesting that we do not even have to resort to DNA damage. DNA damage is associated in this context to nanodosimetry because we perform evaluation of energy depositions at the nanometric scale. Actually, we can also stay with microdosimetry only. What do I mean? I can also calculate an RBE which is purely microdosimetric as far as we introduce a weighting function for the linear energy. The linear energy has been introduced by Hans before, and basically the point is that the highest linear energy component, they have to be weighted with a decreasing biological weight. And this is due to the so-called overkill effect in radiation biology. Basically, if you look at DNA damage as a function of LET, you see that this is happening, let's say, spontaneously. And this is happening because at very high LET, you have fewer damages, but the internal complexity of these damages has been increased. This is not reproduced by microdosimetry. Microdosimetry will give us a quantity that is always increasing. But if you introduce a specific weight for the highest LET component, and this weight is actually thought to reduce their biological effectiveness, then we can also provide a calculation of RBE using only linear energy evaluation. This is a saturation correction for the linear energy in strict terms. And you see again that this is depending on the site of the sensitive size that is chosen. You see again that we can reproduce the trend of the neutron RBE as a function of energy. All of these concepts can be actually applied, as I anticipated in the beginning, to treatment plans. So for instance, the RBE for neutrons that can be computed with either DNA damage or microdosimetry only can be implemented in treatment plans for proton beams in order to have an idea of the RBE of secondary neutrons that are produced as a function of the distance, for instance, from the Bragg peak. So concluding, micro and nanodosimetry approaches with full Monte Carlo simulations can be can constitute an important data set for further implementations and applications for the evaluation of the effectiveness of a mixed radiation field. In particular, to do so, it's actually necessary to be able not to run full simulations again, which suggests the adoption of an approach like the one I've discussed with you, which means having analytical formulas that are actually responsible of reproducing this data without running the full simulation. I briefly introduced which is the methodology that can be developed by which macroscopic radiation transport code can be extended to predict biological effectiveness at the cellular, so microdosimetry, or subcellular, so nanodosimetry levels. And in particular, this approach, I briefly discussed the case of neutrons, but the point is that this approach is actually valid for all possible mixed radiation fields. And as I anticipated in the introduction of the talk, we generally always encounter mixed radiation field, like the case of a therapy, an hadron therapy applications in which the primary beam is undergoing a reaction and producing other species, or the radiation environment in space, or as I told you, the neutron case. Thank you for your attention, and I'll be happy to answer questions.
Thank you very much, Giorgio, for this really very interesting presentation. So now the presentations have finished. As I said, you can write your questions on the public chat, but before starting to talk about these questions, we would like to ask you to answer 2 different polls so we can have an idea of the profile of the audience that is attending the webinar. So you can also see the answers on the poll. So I give you just some minutes to do that. So if you go to the poll part, you can see the answers, the percentage of the different answers. Okay, now going back to the chat, there were a few questions about Hans' presentation that have been already answered by Hans on the chat. I don't know, Hans, if you want to complete some of them, or is it okay?
Well, I think I have answered all of them. There was actually, I saw another one coming up, which was about sharing your slides. I think they will be made available anyway, right?
On the Eurados webpage, I think, as well as the recorded webinar. You can see it again if you're interested in it.
Yeah.
Okay. So I don't see any other new question coming for either Jan or Giorgio. In any case, I think you have their email address. So if some of the people attending have questions coming, and they can contact directly the presenters after the webinar. Okay, I let you maybe 1 or 2 minutes if someone has a present question. Sorry, you don't have micros. You only can write the question on the chat.
So as I have a micro, maybe I can ask a question. It's actually a question to Giorgio. Giorgio, could you comment on the following? In principle, in micro and nanodosimetry, we are dealing with stochastics. So the approach that you showed was basically using the deterministic quantities like dose mean linear energy or something like that. Do you think that this description is complete, or that we don't lose anything when we lose the stochastics?
Well, there's still some stochasticity which is included in the track structure simulations, if you think about that, because the point of the mixed field approach, when we use DNA damage data, is to correlate to a specific value of the LET in the cell nucleus, so of the dose mean linear energy, a DNA damage yield. And that yield has been previously calculated on the basis of full Monte Carlo simulations. So for instance, considering an uncertainty that can be associated to that yield in terms of stochasticity, that is included. Of course, the value with which we characterize the field is a single value. So in that term, we are losing the width of the distribution. But in principle, that could also be included with a more of a probabilistic approach. My feeling is that summing all up, let's say, if the purpose is to characterize the effectiveness of a field going from the macroscopic scale, so needing also the aspect of full transport of the radiation at a macroscopic scale, and then going towards the cell level, then we are not losing much in this sense, because we have all this chain of events at these changing spatial scales. So I would not expect a big influence of considering a width, for instance, on the dose mean linear energy, on the linear energy value associated to each single cell.
Okay, thank you.
Thank you.
Giorgio, there is a question on the chat coming from Ana Selva, which is who is asking for which weighting function did you use for calculating the start, to calculate the RBE starting from the microdosimetric spectra?
Yes, it's the weighting function was actually written explicitly in the slide, and it's the standard weighting function for the saturation correction with different Y0 parameters, and the final plot was obtained with different values of the saturation correction parameter. The full formula is reported in the slide. I don't know if the slide can be shared again, or I think anyhow you will have access to our presentations.
Mm-hmm. There is another question coming from Telma Fonseca. I guess it's for you too, about the time of the simulations.
Do you mean, well, there are different times associated to the different kinds of simulations. So on one side, you have the macroscopic simulations with the radiation transport, and that's actually strongly dependent on the spatial scale of the field that you want to characterize. With neutrons, for instance, I've discussed the neutron examples. This is also largely dependent on neutron energy, because if you have neutrons that are weakly interacting, then to have enough statistics in your macroscopic phantom, you may need to run the transport code simulations for some days. But that depends a lot on the geometry. Concerning track structure simulations, that's a different story, that's a different time, let's say. So the two times have to be summed up if you want. The radiation track, the simulation of the track is not so time consuming. What is actually very much time consuming, as it was also introduced by Jan, is the calculations of the indirect damage component, which means the production of the free radicals, the diffusion of the free radicals, all of the chemical aspects, let's say, up to the final DNA damage induction. The point of the time of the simulation is, of course, very important. So that's one of the idea behind the use of analytical functions to reproduce DNA damage data, because in that specific case, you need to run simulation only once and you have the data available later on.
Yeah, there was she precised after that she was talking about the radiolysis and the chemistry steps. And okay. I think this is one of the problems in all these tracker structure codes, as Jan also explained in his presentation. That is one of the main reasons in GN4 DNA why this new approach of IRT, independent reaction time approach, is used to speed the simulation of the chemical stage, comparing to the step-by-step method that it is in fact used in PowerTrack 2. But of course, the use of parametric data speeds this this time of the simulation as you did. Okay, there are other questions. There's a question from Musa Yusuf Dambele about how we can practically quantify radiobiological damage while carrying out basic radiobiological investigations. This is an important question. Maybe Giorgio, you can give some your opinion about that. Which kind, I would say, which kind of experimental data in radiobiology can be used to quantify this damage that can be then compared to the simulations of the codes?
Okay, so yes, as you say, this is a very important question. I think we need to distinguish, if you want, between the kind of data that are needed to benchmark simulations and the kind of data that are needed to characterize the effectiveness of a given radiation field. Because on one side, to characterize the simulation, we need to benchmark the simulations. We need data that are in the highest possible controlled condition, let me say. This is pretty trivial as an observation. But for instance, just to make a practical example, Jan was mentioning before the difference between hetero and euchromatin domains. So now if we want to benchmark simulations about DNA damage induction in hetero and euchromatin, then we need to have experimental techniques available by which we can focus a particular beam on a region of the genome, and we need to be aware of the compaction level of that genome region. So, for instance, we can think about particular stainings for the compaction level, and we can think about a microbeam experiment. This is going to provide us a series of data by which we can actually benchmark the simulations. On the other end, if we just need, it's a big word, if we need a general endpoint, a radiobiological endpoint by which we can obtain an information about the field effectiveness, well, as you have seen in the neutron case, radiation weighting factors for neutrons, they are obtained from the mix of a variety of endpoints. And still, we see that RBE evaluations based on DNA damage reproduce the trend of this biological effectiveness of this weighting function as a function of energy. And in that weighting function, in that weighting factors, all data are gathered together, like survival data, animal experiments. So it really depends. I mean, the kind of data you want to produce really depends on the use you want to make of those data. I hope I targeted the question, at least partially.
I think it's quite complete. But well, we are arriving to the end of the webinar. Maybe one last question from the chat, a difficult one, maybe addressed to Hans. I don't know. It's from Rick Tanner. He says, ICRP are currently beginning their review of radiobiological protection with view to produce a new recommendation. Is there a realistic possibility that nanodosimetry could have input to the new WR functions, including for low energy photons? It's not an easy one. Hans, your micro is muted. Sorry, you're muted.
I'm sorry. So it's definitely not an easy one. And I just answered in the chat that we should discuss that during the next annual meeting. I personally think there is a chance, particularly for that case of low energy photons. But it requires some work, and it's not something done. I don't know, done on the side. One really has to concentrate on that. It requires some research and some deeper investigations.
Yeah, I agree with you. Yeah, we have 40% of people attending that more or less belong to Eurados, so maybe we can talk to each other about that in the next AM meeting.
Yes, and actually Werner Rühm just wrote in the chat that the ICRP has a task group on RBE and that this topic should be discussed there. And as he is the ICRP chair, I think there should be a good opportunity to do it.
Okay. Well, I think it's time to close. Thank you very much to all of you, the audience, and especially, of course, the presenters. And maybe see you soon. Thank you. Bye.
Thank you. Bye, everybody.
Bye, everybody.